This is number 2 of worksheet 4. Suppose in the icy hot lab that the burner transfers 325,000 joules of energy to 450 grams of liquid water at 20 degrees Celsius. What mass of the water would be boiled away? Let's list out what's happening in the situation. So, in the icy hot lab, we have some liquid water particles that are sliding past each other, and they're being warmed by the Bunsen burner. And from start to finish of this lab, it's going to give the water, it's going to transfer that many joules of energy to the water. Now this water is starting out at 20 degrees Celsius. So my starting temperature is 20 degrees Celsius. We want to find out what mass of the water is going to be boiled away. So that's going to key us in that probably not all 450 grams of liquid water is going to boil. We might warm up the total 450 grams of water, but not all of it's going to boil. We're trying to find out exactly how much of it did boil. So when we draw our heating curve, we want to first identify our initial temperature, and that's 20 degrees Celsius, which is about room temperature. When we first are giving heat, when we're first giving our energy from the Bunsen burner to the water at 20 degrees Celsius, we have to find out if that energy is going to cause a phase change or if it's going to raise the temperature. In order to figure out if it's going to cause a phase change, we need to know that phase changes for water happen only at 0 degrees Celsius and 100 degrees Celsius. At 0 degrees Celsius, we have a solid that can turn into a liquid, or a liquid can turn into a solid. At 100 degrees Celsius, a liquid can turn into the gas, or the gas can turn into the liquid. If we're warming this, it's going to get hotter. And so we can assume that that energy is going to bring that water to its boiling point of 100 degrees Celsius before it can start to boil. Then some of the water will end up boiling, according to the question. So that's going to be a phase change at 100. So from 20 to 100, we have liquid water, and then that liquid water is going to boil and become a gas at 100 degrees. So we want to figure out exactly what mass is going to become a gas. To first do that, I gave you a hint to find out how much energy was required to bring all 450 grams of water to its boiling point. So we need to find out what Q was involved with bringing this water from 20 degrees to 100 degrees. Since we have a temperature change, we know that we're going to have to use Q equals MC delta T for that section. So step 1, let's figure out how much energy it required. So we're going to solve for Q. Our mass is 450 grams. Our C, our little c, is the specific heat of liquid water, since that is what we're warming. And that's going to be 4.18 joules for every gram degree Celsius. And our change in temperature is the difference between our final temperature and our starting temperature. So 100 minus 20 is 80 degrees Celsius. Calculating that out, our Q the amount of energy needed to warm our liquid from 20 to 100 degrees. Now this is going to be a rounded answer, but it's rounded to 150,000 joules of energy. So now we know that 150,000 joules of energy came out of our total energy to warm that liquid. So we need to figure out how much energy is left over to boil this water. So step 2 is finding out how much energy is left over. Take our total amount of energy that the Bunsen burner is going to give us overall, subtract the amount of energy needed to bring the water to its boiling point, and you should get 175,000 joules left to boil the water. Now I gave you a hint to solve for the final mass. You're going to use this energy to solve for how much mass of the water will boil. So we need to solve for mass in our equation. Oh, but what equation are we going to use? Well, from here to here we have a phase change. So we know we're going to use Q equals mH. But are we going to use the heat of vaporization or the heat of fusion? If we're going from a liquid to a gas, we're going to use the heat of vaporization. So I need to rearrange my equation, Q equals mH, heat of vaporization, to solve for m. To do that, all I need to do is get m on the side of the equation all by itself. So I need to divide both sides by my heat of vaporization so that I can move it over and get mass all by itself. And I do that because if I divide something by itself, it's going to cross out. Kind of like how 2 divided by 2 is 1, or 100 divided by 100 is 1. Heat of vaporization divided by heat of vaporization is going to be 1. So my mass is going to be equal to my energy divided by the heat of vaporization of water. Now the energy that I'm going to use is the energy that's left to boil the water. And my heat of vaporization of water is 2,260 joules per gram. Dividing these numbers out, I should find that the total mass of water that's going to boil is 77.4 grams. So that means not all of my water is going to boil, and that's true. During the lab, we didn't let all of the water boil. We only let some of the water boil so that it becomes a gas. Now, another thing that I want to point out is what the difference is between what the energy is going to do to our water particles in each step of this phase diagram. When we're heating up a liquid, its temperature is going to change. If its temperature increases, that must mean the particles are going to start moving faster. So when we have a slanted portion to our heating curves, the temperature is changing. And so that affects the motion of the particles. So that means that energy is going to be stored in my thermal energy account. But what about during phase changes? During phase changes, the energy that's being added is not going to change the temperature. So that means during phase changes, the energy that's being added or removed is not going to affect the speed of the particles. What it's really going to affect is the attractions between particles. You saw that in the What a Gas lab, that a liquid has more attractions than a gas. Because when you dropped a rubber stopper down a graduated cylinder filled with water, it moved slower and fell down slower because it had to get through those attractions of the liquid. So when we add energy to our liquid during a phase change, that must mean that the energy is going to break the attractions of the particles in a liquid so that it can become a gas. Since it's only breaking the attractions between H2O particles, that means that a phase change is not a chemical change. All it's doing is causing the liquid water, the liquid H2O particles, to become gas H2O particles.